Hello. So we're going to start chapter 4.2, which is logarithmic functions. So logarithmic functions. Before we start on logarithmic functions, we need to review inverse functions. So remember, a function has an inverse if it's 1-to-1, if it passes this horizontal line test, if you remember this from earlier. And if we look at an example of a exponential function, like this one here, we can see that it does pass the horizontal line test. See, no matter what horizontal line you draw, it only crosses once. So it is a function, and it is 1-to-1, so it should have an inverse. So typically, when we're trying to find an inverse, we switch the x and the y. So if we have this function, y equals, say, e to the x, and we want to find its inverse, we'd switch, if we're going to find the inverse, we switch the x and the y, and we solve for y. Remember doing this, finding inverses. Okay, well the question is how do we solve for y? How do we get this y unattached, which is an exponent from the e? Okay, and is there a function that does that can put the y in front? So we have y equals some function of x. Okay, we're wanting to get from here to there, right? Well, how do we do that? And that's really the question of this search for this logarithm. Logarithms are inverses of exponential functions. Okay. So when we have an inverse, what are properties of inverse? Can we name some of the properties that we know of functions? Well, we know some properties of inverse. We know that, first of all, the domain of the first function becomes the range of the inverse function, okay? And the range of the first function becomes the domain of the inverse. And if you remember the domain of the exponential functions, the domain is all real numbers. So that's going to become the range. Okay, that's going to become the range of the inverse. Okay, well, what's the range? Well, the range is from 0 to infinity, and that's going to become the new domain. Okay, so we know those properties. So we know that while the exponential function has no restrictions on the domain, the inverse, this inverse of this exponential function, which we're going to call logarithmic functions or logs, they will have a restriction on the domain. The domain's going to be restricted. So we can get that right from the bat. Okay. Well, how do we define these? What's the definition? Do we have a definition for the inverse? Well, definition of a logarithmic function of log base x equals y, okay? So we have this function here, logarithmic function. It is such that we're solving this equation, b of y equals x, okay? So that's really the definition of this logarithm is you're solving whatever value of y, when you raise b to that value, you get x. So let's start with some simple examples. So example 1, we have y equals 2 to the third. Now, what is this written in? This is an exponential form. What is it in logarithmic? Well, here's your base. Okay, and the base is going to go here. This is going to be your y, and this is going to be your x. Okay, so when we transfer this, this will be log base 2 of y equals 3. Okay. Okay, what about this next example? 125 equals 5 to the third. How do we rewrite this? It's in exponential form. What about logarithmic form? Well, in logarithmic form, it's going to be log base 5, because here's the base, of 125 equals 3. So it's saying log base 5 of 125 equals 3, which means that 5 to the third equals 125 is what that's stating. Okay. Last example here, we have I don't know, 3 to the fifth equals 243. How do we rewrite that in log form? It's going to be log base 3 of 243. It's going to equal 5. Okay. What about going the other direction? Say we want to go, so up above we went from exponential to logarithmic form. So what about from, next example, from logarithmic to exponential form? Okay, well, let's say we have 2 equals log y of 16. What is this? So here's our base, here's our exponent, and here is what it equals. So your base, exponent, what it equals, okay? So when we rewrite this in standard exponential form, it's going to be y to the second equals 16. So what is y in this case? Well, y would equal 4. Now you're saying, well, what about negative 4? Because negative 4 in parentheses squared also equals 16. That is true, but for our case, if we remember, that's why I talked about the domain first. The domain of the inverse function is equal to the range of the first function, and for your standard logs, their domains are 0 to infinity, so we're not including negatives in this. So for standard logs. Okay, so let's look at evaluating some of these logarithms. So let's say they want you to evaluate. Say log base 2 to the 16. So they're asking you what power, what you're being asked to really solve this. 2 to the x equals 16. What is the value of x that makes this true? So when we raise 2 to what power it equals 16? Well, that would be 4. So then log 2 to the 16th equals 4, because 2 to the 4 equals 16. All right? Okay, what about another one? What about log 7 equals 149? Well, log 7, 149, what are we really solving? We're saying we're solving this equation here. Okay, we can see that this is going to return a value of negative 2. Okay, so because and the reason for this is 7 to the negative 2 equals 1 over 7 squared, which is 1 over 49. Okay, let's do another one. Evaluate this. Okay, well, we're solving this. 25 to the y equals 5th. What value of this is? Well, if we take the square root of 25 equals 5, so then y would equal square root, or 1/2. So the solution to this is 1/2. couple more examples. What about log 7 to the 7? Well, what are we solving here? We're solving 7y equals 7. What's the value of y that makes this true? Well, that's going to be 1. Y equals 1, right? So then log 7 to the 7 equals 1. And in fact, log a to the a always equals 1. So anytime you have a base a and you're taking log base a to the a, it's going to equal 1. So log 10 to the 10 is going to equal 1. Log 3 to the 3 is going to equal 1, etc. Okay. What about another quick example? What about log base 5, 1? Well, from this we're solving 5 to the what power equals 1. Well, this is easy. This is going to equal 0. Y equals 0, because anything to the 0th power equals 1. So this is another example that'll hold. So anytime you have log any base to the 1, the answer is 0. Okay, 1 equals 0. That's for any base. Okay. So those are kind of two properties that we have. First property that we're getting that's general, true for all logarithms, is log base b to the b equals 1. That's property 1. Property 2 is log base b to the 0, or to the 1, equals 0. Excuse me. Okay, so those are two properties no matter what the base is. Okay, now let's talk about another property. So these are two properties of logs. We also have the inverse. The whole point of talking about logs was to find an inverse of the exponential function. Okay, and so we have inverse properties of logs. So inverse properties of logs. Log to the b to the bx equals x. If we notice here, this property is true. So it's saying when you, in order for them to be inverses, if you plug the function into itself, so f of x equals b to the x, that's your exponential, okay? And we're saying the inverse of it is g to the x equals log b to the x, right? So if we plug f of x into g of x, if we have g of f of x, if they're inverses, this should equal x, right? That's the property of inverses. So we're stated that these are inverses. This is how we've defined a logarithmic, is it's an inverse of an exponential. So then by definition, the above will be true. So by this definition, this above will be true. This is true. Because we've used the definition to define what a log is. Okay, equally true, f of g of x equals x for inverses. So then if we plug g of x into f, you'll get b to the log b of x has to equal x. Well, this is also true, because again, this is how we've defined log as the inverse of exponential. So these are two more properties that we have. Okay, so let's look at how this works. An example. So we have log to the 4 5/5. This is going to equal 5 by definition. Okay. Another example of how this is going to work. Say we have 6 log 6 to the 3. This will equal 3. Okay. So you can think of them as inverses. These cancel. All that's left here is a 5. They're inverses. These cancel. All that's left is a 3. Okay. So that's the definition of inverses. And since we've defined logarithm as the inverse of an exponential function, it has to be true by definition. Okay, so now we come to graphing. What does the graph of an exponential look like? So what does it look like? Well, what we need to do in order to graph an exponential is we need to first take or graph a logarithm, and we first need to look at an exponential, okay? So let's look at 2 to the x. So y equals 2 to the x, right? This is your standard exponential function, right? And let's look at its coordinates for x and y. And we remember this from last time. I'll just write it down quickly here. All right. Two, 4, 8. So here is a table for the exponential. Now, because we've defined logarithm as the inverse of an exponential, it means we're switching x and y's, right? We're switching these. So if we're going to graph the exponential, so we want to graph y equals log 2 of x, we're going to switch the x and the y. So on this one, x is going to become 1/8, 1/4, 1/2, 0, 2, 4, 8, and y is going to become -3, -2, -1. Oh wait, this should have been here. This should have been 1 here. My bad. Should have been 1. Which makes that 1, 0, 1, 2, and 3. Okay, and then we'll graph this, and when you graph this, what you're going to end up doing is all logarithmics are going to cross at 1 here in their standard form. Okay, and it's going to look something like that, minus the bumps here. Let's try it again. See if I can get a steadier hand. Ah, my bad. Try again. Like that. So that will be your logarithmic. Okay. And you can plot the points like this will be 3 here, and where it meets will be at 8. It'll match up according when you switch the graphs here. Okay. All right, let's continue talking about graphs. So for graphs, let's talk about some simple examples here. What about, let's look at varying the bases. So if your base b is greater than 1, if your base b is greater than 1, then what you have is here will be the exponential for y equals b to the x. Here will be the logarithmic. This is y equals log b to the x, okay? So we've graphed, that's with base b, okay? Now what about if the base b is between 0 and 1 somewhere? Well then, if you're going to do that, remember this case for our exponential, they are descending like this. This is 1, like this one, then this guy will descend like that, and you'll have, this is y equals x, this will be your log b to the x, this will be your y equals b to the x, okay? So we already talked about the domain and range. So the domain of a logarithmic is 0 to infinity. The range is all real numbers. Okay, and you can see that looking at the graph. Now you can change the domain. The range isn't going to change really unless you do something like fancy. I mean, you could change it with certain values. But for any linear arrangement, you're not going to change the range. But you can move the domain up or down, okay? You can shift the domain maybe to the, say you want to shift it to the left, so the domain is -3 to infinity. Well, you do that by doing log base b x plus 3. This is a shift to the left. You want to do a shift to the right. It's going to be log base b x minus 3. Okay, that'll be a shift to the right, so the domain is 3 to infinity. Okay, so there's shifts to the left and right. I won't look at other shifts. They're going to just function the same way. Like you want to go up and down, you just add or subtract the outside, right? If you want to make it thinner or fatter, you'd multiply by numbers up front, etc. Okay. So let's move on. We're typically looking at two bases. We're going to have base 10 and base e. Okay, e, remember, is a number. We talked about it last time. It's like 2.71 ... Okay, and those will be our typical bases that we use. Okay, and we will talk about how to switch between bases, etc. In chapter 4.3. But for now, we're just doing introduction to logs. Let's look at some other practical examples now where we're going to solve this. So I'm going to just pick a couple from the book. Example 1 is modeling the percent of a child's height. So in this example, they want to know what's the percentage that your child height is completed growing. Like, if your child's 5, how much has she completed her growing, or he, this is for boys, completed his growing, and they have this function. Okay. And what this is it tells you the percentage of the height your child's completed growing at certain ages, where X is in years. So this is years. So you want to know how much of your child's height have they grown at, say, age 8. Well, then you plug 8 into X. All right. Okay, and then we have to calculate this. Now, before I move over to a calculator to show you how to do this, anytime you don't have a base written, normally if you have a base written here, if it's not written and it's a log, then it's be base 10. So this is understood to be base 10 here. It's not written, but it's understood to be 10. Now, you can understand to be base e as well, but how you write logs with base e is with the word ln. If you've seen the word ln, ln, that's log base e. So this is really log base e, okay? It's just that we use log base e so much that we made it its own thing, just to avoid writing log. This is so much shorter than this, okay? That's just a note here. So now I'm going to go in and show you how to calculate this. So I'm going to have to switch over to my calculator. So here I have a calculator. I made sure I pulled one up this time. And it has log base 10. You can see it in the center here. And so what you're going to do is you're going to plug in 29 plus 48.8 times, you push log, oh, see, it doesn't work here. So this is not your normal scientific, so we're gonna have to do the log first. So what you do here is plug in 9 log, and it's clear. It's not working. Let's try it again. So this is why you have to figure out what kind of calculator you're using. So you're gonna do 9 log. Yeah, so 9 log. All right, equals that. Then you multiply that by 48.8, enter, and add 29, enter, and you get 75.5. So that means, since we've been told this is in parentheses, that your child is 75.5% done growing as far as height. Okay, so this is simple how it works. Another example let's look at is called the Richter scale. This is how you measure intensity of earthquakes. Okay, the formula for the Richter scale is R equals log I over I naught. And what they've done here is I naught is this earthquake that happened over 100 years ago. It's barely, you can barely feel it, and they kind of call that your base earthquake. And what you're going to do, and this is again log base 10, you can notice here, what you're going to do is you're going to compare every earthquake, all its intensity, to that earthquake. So let's say you have an earthquake that is 10 to the 8th. So it is, what's 10 to the 8th? 10 to the 8th is, there we go. So it's a 10 to the 8th. We have 8 zeros here, right? 1, 2, 3, 4, 5, 6, 7, 8. So 10 to the 8th I naught. So I naught is an earthquake that you can't really feel, like it's barely feel. It's kind of the most basic earthquake. Let's say we have an earthquake that's 100 million times more intense than that original base earthquake. Then what is its Richter scale on the Richter scale? So you're going to plug it in. Do the Richter scale equals log 10 to the 8th I0 over I0, all right? Your I0s cancel out, and you're left with log 10 to the 8th. Now this, remember that from our example, that the log and 10 to the 8th, they're inverses of each other, so these cancel, and we just get 8. So it's a measure of 8 on the Richter scale. So when you say you have an earthquake that's a measure 8 on the Richter scale, you really mean that it's 100 million times more intense than that base earthquake that you felt that can barely be felt. So when we say a Richter has a 9 on the Richter scale, we mean it's a billion times more intense than this base earthquake. Okay, so Richter scales go up in factors of 10. All right. In closing, I'm just going to go through again the basic properties of logs that you have to know from this chapter. So here's properties of logs. You have log b to the 1 equals 0. In the same sense, ln of 1 equals 0. Okay, log b equals 1, so ln b to the b equals 1. Ln of e equals 1. Okay, and then we have the inverse properties. Log b to the x equals x, so ln e to the x equals x. And then b log b to the x equals x, and e ln x equals x. So these are inverse properties here. Here's your other basic properties, and these are the basic properties we're going to carry through into the next section. Sorry for the chainsaw that was going outside. Hope to